In this video, we're going to work with the algebraic algorithm of linear programming, Simplex method, in order to solve the prototype example. Last video, we worked with the geometric algorithm. In the geometric algorithm, we started with the initialization step where we choose the double O start point that was the origin, and then we do an optimality test over here. We just jump directly to it. And here we check if there was a better adjacent CPF solution. And if there wasn't any better adjacent CPF solution, we went all over the 3 steps algorithm. So we got here step 1, we choose the edge. Step 2, we stop at the next restriction. And step 3, we solve again the intersection. And then we had again the optimality test. We did 2 iterations in order to get the final solution, the optimal solution. Regarding algebraic algorithm, we're going to be also having more or less the same algorithm. We're going to have initialization, but at this point we're going to be choosing the double O for x1 and x2, and we're going to be calling them non-basic variables. Then we jump directly to the optimality test, and here we're going to be looking forward for positive coefficients. If we still have positive coefficients in the objective function, then we start with the iterations. Okay, step 1, determining the direction. Step 2, determining where to stop. And step 3, solving for the new BF solution. So when we're back, we're gonna do again the same questioning if there are negative values. So we're gonna be doing 2 iterations. And finally, when we don't have any positive coefficients, then that means we are at the optimal solution. Before we start, remember that we did some changes to the model, to the original form of the model. Okay, in order to change this less equal signs, we introduced slack variables so that we were able to have equal signs. Okay, so for the initialization, starting with this augmented model, in the initialization we're going to be choosing x1 and x2 as the non-basic variables. Non-basic variables, they're going to be always equal to 0. So we choose them as being equal to 0, and then we can now solve the equation. This one becomes 0, so we have now that x3 equals 4, x4 equals 12, and x5 equals 18. We have 3 equations with 3 variables in the system of equations, and now we can solve it. So now my system x1, x2, x3, and x4 plus x5, the values are going to be 0, 0, 4, 12, 18. Okay, so we pass to our next step. Our next step is the optimality test. At this point, the main criteria for decision is the one that we got here in blue. If we have positive coefficients in our objective function, that means that we can still have a better solution. That's not our optimal solution. Okay, so at this point we got 2 positive coefficients, so that means that this is not our current optimal solution. Okay, now solving at this point, we have 3 x1 equals 0. Okay, so it's going to be 0 plus 5, 0, z at this point, values 0. So that means we're going to start with one iteration, and we go to step 1. Iteration 1, step 1. Same as we did with the geometric algorithm, we're going to look forward to determine which direction should we go. Remember, we take our original objective function here, 3x1 plus 5x2. If we increase 1 unit in x1, we're going to be able to enhance z in 3 units. if we change x2 per 1 unit, we're going to be able to enhance z in 5 units. So we're going to go through x2. That means that x1 stays as 0, this one still being a non-basic variable. But now x2 will become what we call an entering basic variable. It's not more anymore a non-basic variable. This, we're gonna change it with another basic, whether we're gonna be changing places with another basic variable. Iteration 1, step 2, determine where to stop. At this point, we know that now x2, it's my entering basic variable, and we want to know how far can x2 can go. So we got to do some math in order to determine this, and what we're going to be applying is what we call the minimum radial test. So x1, it's equals 0, so this x1s are gone, and what we're going to have here is going to be x3, okay, equal 4, and then we got 2x2 plus x4 equal 12, and then we got 2x2 plus x5 equal 18. Okay, now we are not really right now interested in working with our other variables. We want to know how far can we go to x2, so we're going to move this 2x2 to the other side, and what we're going to get is x3 is going to be equal to 4, x4 is going to be equal to 12 minus 2x2, and x5 is going to be equal to 18 minus 2x2. And we're going to work only with this part of the equation. We're going to say that this is greater or equal to 0, greater or equal to 0, greater or equal to 0. And this will let us know how far can we go with x2. So we got 4 is greater or equal to 0, and then we got 12 is going to be less or equal to 2x2. So we got here that 6 is less or equal to, or let's put it the opposite way, x2 is going to be less or equal to 6. And we also have 18 is going to be greater or equal to 2x2. So what we got here is that x2 is going to be less or equal to 9. At this point, as the minimum radial test, we're going to state with the minimum value. That means for 6. Okay? Why? Let me demonstrate you why. If I take the restrictions I just have over here, this one, 12, okay, no, sorry, this one, 12 minus 2x2 greater or equal to 6. If I change the x2 with 6, I don't have problem, it accomplished. Now for 18 minus 2x2 greater or equal to 0, if I change the 2x2 with 6, I still don't have problem because it's 18 minus 12, we got 6. So we accomplished the restrictions. Now regarding 9, if I change x2 with 9, I will have 12 minus 18. This will be minus 7, no, minus 6. And we're not accomplishing this restriction. This one, yes. Okay, now because of that, we're going to stay then with the minimum value here. And that means that at this point, after choosing 6 as the minimum value, what we got here, if we follow this line, we're going to see that this is related with x4. Okay, so what we're going to be doing is, we say before that x2 is my entering basic variable, and now x4 will become my leaving basic variable. That means we're going to be switching places between these two variables. x4 will become a non-basic variable equal to 0, and x2 will become a basic variable. For that, we go to step number 3 in iteration number 1, and here in order to be able to do this switching between x2 and x4, okay, we got to do what we call Gaussians eliminations, okay? When we do Gaussian eliminations, what we're looking for is the pattern that we got here for x4, and the pattern is 0, 0, 1, 0. It will become also the pattern for x2, 0, 0, 1, 0. Right now, my pattern is of 5, 0, 2, 2. So I got to do some algebra in order to be able to make all these eliminations and have the new pattern for x2. So how are we going to be doing this? How are we going to be able to put this 0, 0, 1 pattern in x2, 0, 0, 1 pattern? Okay, so we're gonna be working for each equation. Our first equation is we want to do this change between x2 and x4. And the equation that has those two variables, it's equation number 2. So we're going to start mainly with equation number 2. Equation number 2, it's 2x2 plus x4 equal 12. That means we got a 2, and we need that this coefficient of 2 becomes 1. So the easy way to do that is by dividing by 2. We got that 2x2 divided by 2x2 plus 1/2 of x4 equals 6. Okay, this will become my new 2 apostrophe function, restriction function, and it's exactly the one that we got over here. Okay, the other three, so we have done with 2 and 2 apostrophe. The other three restrictions will be changed using either 2 function 2 or 2 apostrophe. Okay, we must do it through them. That's a condition for this Gaussian elimination. So let's start with equation 0. We got z minus 3x1 minus 5x2 equal 0. And we need this 5 to become 0. We got 0 here, we got the 5, so we need this one to change it by 0. So here at this point, we can use this equation number 2 apostrophe, and if we multiply it by 5, watch what we got. We're going to have plus 5x2 plus 5/2 of x4 equal 30. Okay, so my new equation 0 apostrophe will be z minus 3x1 plus 5/2 of x4 equal 30. These two are eliminated, so now x2 will have 0, okay? And this equation that is here is exactly the one that we got over here, okay? So we have done with this with equation 0. Now, the next one, it's quite easy because if you see what we got here is mainly that for equation number 1, we need a 0, and we already have a 0, so we're not going to do anything else but just copy exactly the same equation, okay? And that way we got 0, 0, 1. Now we got to work with equation number 3. Okay, for equation number 3, what we got is 3x1 plus 2x2 plus x4 equal 12. This 2 we have here, sorry, this is x5 equal 18. So here, this 2 must become 0, okay? So we're going to be working with equation 2, okay, but minus. So we put minus 2x2 minus x4 equal minus 12. And we add them at this point, okay? And what we're gonna get, it's 3x1, 0, these two are eliminated, minus x4 plus x5 equal 6. And this equation is the one that we got over here. So what we have done is this pattern, now we have it exactly here. And after doing this, at this point, with this new system of equations, what we have is x1 equals 0 and x4 equals 0. These are going to be our non-basic variables. Okay, so let's go and finish this point and solve our BF equations. So using the new system of equations, what we got is this x1 and this x4 are 0, so we're going to have now that x3 is going to be equal to 4, x5, x2 is going to be equal to 6, and x5 is going to be equal to 6. So we got x1, x2, x3, x4, and x5. Their values are going to be 0, 6, 4, 0, 6. And if I apply these values to my formula, okay, at this point is z minus 3x1 plus 5 halves of x4 equal 30. Let's leave z from the other side of the sign, so we're going to have 30 plus 3x1 minus 5 halves of x4. Okay, x1 it's equal to 0, x4 it's equal to 0, so z at this point values 30. Okay, now after doing the last step, we're back to our optimality test. And remember, we're looking for positive coefficients, where we have before minus 3x1 plus 5 halves of x4 equals 30. So we put z from the other side of the equal sign, and this is going to be 30 plus 3x1 minus 5 halves of x4, and we do still have one positive sign. Okay, so we got to do another loop. We're still not yet in our optimal value. So let's go to iteration number 2, step 1. Here we got to decide in which direction should we go. So taking our new objective function, 3x1 minus 5 halves of x4, if I increase 1 unit in x1, I'll be able to enhance my objective function in 3 units. And if I change x4 with 1 unit, it's going to be negative. So this is definitely not an option. That means that x1 now will become the new entering basic value. x4 stays exactly the same, equals 0, and this is the non-basic variable. At this point, now let's go to iteration number 2, step 2, where we want to know how far we got to go. Now, we say that x1 as my entering basic variable, we want to know how far can we go with it, okay? So, and we also know that x4 is equal to 0. So the x4s here become 0, and what we're gonna get here is we're gonna have in our new formulas, it's x1 plus x3 equal 4, and then we got x2 equals 6, and here we got 3x1 plus x5 equal 6. Okay, so from here we're going to have x3 is going to be equal to 4 minus x1, and x2 is going to be equal to 6, and x5 is going to be equal to 6 minus 3x1. we want to know how far can we go with these x1s. Okay, so we are going to take only that part of the square and put 4 minus x1 less or equal to 0, 6 less equal to 0, and 6 minus 3x1 less equal to 0. This one doesn't have x1, so we're not going to work on this one. For the first one, this one, what we have is that x1 is going to be less or equal to 4. And for this one, we can say that x1 here is going to be less or equal to 2. Between these two numbers, 2 is the minimum value, okay? And these two send us directly with the x5. So that means that x5 will become now my living basic variable. That means we're going to be switching between x1 and x5 through Gaussians elimination. That means that the pattern that we got here, we got to bring it now over here through Gaussians eliminations. Now, we say we're going to be doing x1 exchanging with x5. And the equations that have both variables, it's for equation number 3. So we're going to take this equation 3 apostrophe. It's 3x1 minus x4 plus x5 equal 6. We need that this 3 becomes 1 here, okay? So this 3 needs to become 1. And the way we can do it is dividing all the functions by 3. So we're going to have our new 3 double apostrophe is going to be x1 minus 1/3 of x4 plus 1/3 of x5 equal 2. And this is the equation that we got here in the bottom. Okay, now we can work the other ones, but remember, in order to solve them, we got to use either equation 3 apostrophe or 3 double apostrophe. So let's solve now equation 0. Okay, we got equation 0 apostrophe, it's equal to c minus 3x1 plus 5/2 of x4, and this is equal to 30. Okay, and now what we need here is this, we got a 3, we need to make it a 0, so we can use our original. Here we got a 3, and if we put it negative, then we're going to be able to, well, we don't even need it negative, it's already negative, so we just add it. Okay, that means if we add equation 3 apostrophe here directly, we're going to have plus 3x1 minus x4 plus x5 equals 6. So let's add, and what we're going to have, it's our equation 0 double apostrophe, it's going to be 0. These two are eliminated, and now we got 5/2 plus 1 minus 1, sorry, that becomes 3/2 of x4 plus x5 equal 30 plus 6, 36, and this is the equation that we got here. So at this point we have been able to get our new equation for O, for O double apostrophe. Next one. Okay, for equation number 1 apostrophe, here we have a 0, and we need to have a 0, and we have a 1. We got x1 plus x3 equal 4. This one that we got here must become 0. Okay, so in this occasion, I'm going to be using 3 apostrophe, and what I'm going to do, I'm going to multiply it by minus 1. So we got here 3 apostrophe, double apostrophe, minus, okay, so I'm going to have minus x1 plus 1/3 of x4 minus 1/3 of x5. This is equal to minus 2. Okay, so we add, and these two are eliminated. Okay, and we're gonna have plus x3 plus 1/3 of x4 minus 1/3 of x5 equal 2. And that's what we got here in equation 1 apostrophe, 1 double apostrophe. So that way we have solved this situation. Now we got one last equation that will be 2 apostrophe. In 2 apostrophe, we got here a 0 and we need a 0. So we don't really have to do so much. We just bring it directly and it will stay exactly the same. So now we have our new system of equations. Okay, so if you see this pattern, now we got it over here where we got 0, 0, 0, 1, we got 0, 0, 0, 1. Okay, so our values for x1, x2, x3, x4, and x5, remember that at this point x3 was x4 and x5 were our non-basic variables. That means they're equal to 0. Okay, so this, and this are eliminated. Okay, that's what we got over here, down here. And from these equations, what we're going to have is that x1 it's equal to 2. Okay, x2 it's equal to 6, and x3 it's equal to 2. And these ones become also 0. So this is going to be my new BF solution. Okay, and now these two are my non-basic variables, and these three are my basic variables. We have finished iteration number 2, step 3, so now we're back to the optimality test. Here at the optimality test, we take our function 0 double apostrophe, that it's z plus 3/2 of x4 plus x5 equals 36. Now we need to have the z on the other side of the equal sign, so it's going to be 36 minus 3/2 of x4 plus x5, sorry, minus x5 minus x5. Okay, so we got now only negative coefficients. So at this point, we can say this is our optimal solution. Okay, let's put the value. So we got 36 minus 3/2 of x4. x4 is equal 0 minus x5, and x5 it's a non-basic variable. It's also 0. So z it's now at this point equal 36. And with this, we have finished our problem case. Okay. Now, we have developed then an algorithm, an algebraic algorithm that it's based on mathematical or algebraic, and this algebraic model can we bring it to a computer procedure. And this is just to summarize to a summary of the step what we have done. We did initialization, and in the initialization x1 and x2 become the non-basic variables. We did our optimality test where we look for positive coefficients, and we decided there were no that was not our optimal solution. Then we did the 3 steps of the algorithm. Okay, here we apply them. Here we define the which would be our entering non-basic variable, our entering basic variable, and with the minimum radio test, we define our leaving basic variable. And then what we did is we, through Gaussians eliminations, do the changing of both variables. And then we went back to our optimality test, where we saw it was not optimal because we still have one coefficient that was positive. So we went exactly through our 3 steps until the last optimality test, we saw that it was our optimal solution. Finally, I just want to mention that a great part of this video is based on chapter 4.3, the algebra of the simplex method, from the book Introduction to Operation Research from Frederick Hillier and Gerard Lieberman. Thank you very much.